Hello, everyone. My name is Robert Paxton. I'm the VP of Strategy and Performance for CTA Canada. Firstly, I'd like to thank everyone for attending our Rotating Machinery webinar. With over 200 participants, we really have excellent representation from across the industry. I'd like to first cover some housekeeping items before introducing the presenters and the agenda for the webinar. Please note that this session is being recorded, and we will send all attendees a follow-up email after the presentation with a copy of the recorded session. That email will include a very short survey. It should only take about 2 minutes to complete, and we'd be very grateful for your feedback. Just so that you're aware, all attendees are muted. However, if you do have a question that you'd like answered, please type it in the questions section in the drop-down menu. Regarding continuing education credits, this presentation is approved for CE credits in Alberta, and we'll provide an email address for you to contact to receive your credits at the end of the presentation. In regards to the presentation itself, we're excited to share it with you today. It's a collaboration between our Canadian and UK teams, and we hope to share perspectives from different geographic regions will be helpful for you. CTA has a great deal of global expertise with offices in over 30 countries, so we'll be looking to share local knowledge and global expertise with you moving forward. The agenda for this webinar will start with an overview of power production and various thermal power generation facilities. We'll then move on to explaining the inner workings of a turbine, common failure mechanisms, and adjusting issues. And then we have a Canadian case study with discussion on cause, cost, and policy review. Finally, we'll have roughly 10 minutes to answer any questions you have. So we have 3 presenters for you today. Our first presenter is Joel Edworthy. Joel is a senior adjuster who's based in our Calgary office. He's a professional engineer and has been an independent adjuster for just over 8 years. Joel's areas of expertise are energy and industrial losses, with expertise in property damage, business interruption, third party, and property liability losses. Our second presenter is James Marks. James is a loss adjuster based in our London, UK office. He's been an independent adjuster for over 7 years, and his areas of expertise are power generation and distribution, business interruption, refining and petrochemical losses, with a focus on gas and steam turbine losses. And our third presenter is Bob Moore. Bob is a managing director for Charles Taylor Adjusting in Canada, and he's based in our Calgary office. He's been an independent adjuster for over 30 years, and his areas of expertise are upstream and downstream energy losses, control of well, utilities, cause of construction, wrap-up, pollution liability, commercial and industrial property, and business interruption. So now I'd like to hand over to my colleague, Joel Edworthy, to start the presentation. Thank you.
Thank you, Robert. Hello, everyone. My name is Joel Edworthy. We're going to start the presentation with a discussion on global power production. As you can see, the majority of global power produced comes from thermal sources, coal, gas, and nuclear, making up approximately 70% of all global power produced. We will discuss all 3 fuel sources a little later. Now, if we look at Canada, thermal power production drops from 70% to 33%. By far, the largest amount of power produced in Canada comes from hydroelectric dams. The image on the left shows the concentration of hydro facilities across central and eastern Canada. I'm an engineer and I love numbers and performing analyses. This chart here shows the power usage by province. When you compare percent population to energy uses, the 2 figures align for most provinces until you get to Ontario and Quebec. Ontario has approximately 40% of the Canadian population, however, use only 27% of the energy produced, whereas Quebec has 23% of the population, but uses 35% of the power produced. I'm assuming this is due to residential heating in Quebec, but if someone knows, please put it in the chat box. If you are a numbers nerd like me, you can also look up live power production and live power usage for your province. The image shown here is a screenshot of the Ontario grid one evening last week. As you can see, the majority of power produced in Ontario at the time was by nuclear. Links to the Ontario grid and the Alberta grid are provided below. Now, before we get too far into the presentation, we're going to have to go back to our school days. This may be recently for some or decades ago for others. We're going to discuss the thermodynamic cycle, which converts heat into mechanical energy, the Rankine cycle. In the diagram, you can see at number 1, there's mechanical work put into the system. This is done by pumping water into the boiler. This is represented by W pump. By applying thermal energy, this is represented by Q in, the water undergoes a phase transition from a liquid to a vapor. The steam expands through the turbine as the pressure drops, creating useful work or kinetic energy out of the system. This is represented as W turbine. The vapor is then cooled in a heat exchanger represented as Q out and causing another phase transition from a vapor to a liquid. Typically, thermal facilities are located by large bodies of water to facilitate cooling. The first thermal fuel source we will be discussing today is coal. As you can see from the figures on the slide, coal is used extensively around the world for power generation. It is used primarily in developing countries, however, continues to be extensively used in Nova Scotia, Saskatchewan, and Alberta. Due to our environmental regulations in Canada, our coal-fired plants emit significantly less greenhouse gases than those in countries with less stringent regulations. However, there is a general mandate to retire coal-fired plants across the country. For example, TransAlta in Alberta will be retiring all of their coal-fired plants and converting them to gas-fired plants in the coming years. Here's an image showing the process flow of a coal-fired power plant. In Alberta, many coal-fired plants are built near coal mines to eliminate the cost of transporting the fuel. The coal is crushed and fed into a burner, which heats the boiler. As the thermal energy is transferred to the boiler, the water in the boiler transitions into a steam. The steam then expands through the steam turbine, converting the thermal energy into kinetic energy. As the turbine rotates along its axis, it drives the generator, creating electricity. The steam is then cooled and condensed and pumped back into the boiler. Efficiency of many coal plants in more developed nations is around 43%. However, the global average efficiency is much lower at around 33%. The second thermal fuel source we will be discussing today is uranium. Generally, people are put off power plants by large clouds being emitted from large concrete towers similar to the photo here. First, it should be noted that the nuclear reaction occurring is contained within a closed system. The cloud shown in the image here is purely steam from the cooling process. In fact, a coal-fired plant can release as much as 100 times more radiation into the atmosphere than a nuclear power plant when generating the same amount of power. Canada is the second largest producer of uranium in the world and the sixth largest power producer from nuclear plants. The Bruce Power Nuclear Generating Facility in Ontario is currently the largest operating nuclear plant in the world at 6,400 megawatts. That is enough power to provide electricity to about 30% of all households in Ontario. Several European countries, such as France and Germany, generate the majority of their power from nuclear. In fact, nuclear accounts for 75% of France's power requirements. However, it should be noted that France is in the midst of transitioning away from nuclear to renewable sources. Due to the nuclear incidences at 3 Mile Island, Chernobyl, and Fukushima, many governments face large public opposition to nuclear power facilities. One of the primary benefits of nuclear is the energy density of uranium. One uranium pellet the size of your fingertip has the same energy as 17,000 cubic feet of natural gas, 3.5 barrels of oil, or 1 ton of coal. Nuclear facilities currently have high capital costs but lower direct fuel costs. However, this is somewhat offset by spent fuel management. It should be noted that nuclear facilities are typically used for base loading due to their complexity to bring online and offline rather than to meet peak power demand. Nuclear reactors rely on a fission reaction to produce heat. In a simplified form, a nuclear power plant produces electricity the same way as a coal-fired plant. The nuclear fission reaction produces extreme heat. This thermal energy is transferred to a steam generator. The produced steam drives a steam turbine, which in turn drives a generator, which produces electricity. As you can see here, the fission reaction, and the Rankine cycle are both closed-looped systems. These closed loops ensure that there is no radiation transfer outside of the reactor itself. The thermal efficiency of a nuclear plant is around 35%, with more modern plants achieving up to 45%. The third thermal fuel source we will be discussing today is natural gas. As you can see, gas production accounts for nearly a quarter of the global power produced. Higher thermal efficiencies can be achieved with comparatively low capital costs. In addition, natural gas has relatively low CO2 compared with other fossil fuels. Although natural gas only accounts for approximately 10% of Canada's power production, it is a significant portion of power produced in both Alberta and Saskatchewan. Both of these provinces have an abundant source of natural gas, as well as a significant pipeline infrastructure. The two primary types of natural gas power generation we will be discussing today are simple cycle and combined cycle. This is a simple cycle gas turbine arrangement with one turbine and one generator. With a simple cycle, a turbine is only 35 to 40% efficient due to a significant loss of heat from the exhaust. Exhaust temperatures can be in excess of 600 degrees centigrade. Due to the low efficiency of the simple cycle process, this is not commonly used in commercial operations. When simple cycle plants are implemented, they are primarily used to meet peak power demands due to their ability to come online and offline quickly. To increase the thermal efficiency on a gas turbine, a combined cycle configuration can be used. In simple terms, a combined cycle power plant uses both gas and a steam turbine to generate up to 50% more electricity from the same fuel when compared to a simple cycle plant. An example of this is provided herein. This system utilizes 2 gas turbines and 1 steam turbine. However, a combined cycle plant can have infinite configurations of this. In this system, rather than the exhaust from the gas turbine being vented to atmosphere, it is sent to a heat recovery steam generator where the thermal energy is transferred to the water, creating steam. The steam created from the 2 heat recovery steam generators are sent to a steam turbine for additional power generation. Compared to the efficiency of coal, which on average is 33%, and nuclear, which is around 35%, the combined cycle provides excellent efficiency as high as 60%. The output of a combined cycle plant similar to this configuration is around 900 megawatts. For comparison, the largest offshore wind turbine, GE's Haliade X, produces 12 megawatts. It would therefore take 75 turbines to produce the same power output as this combined cycle plant. Similar to a combined cycle plant in Alberta, cogeneration units can be used. A cogeneration or cogen unit are extensively used in the oil sands. This is the best schematic I have found of a cogen unit. It is from TC Energy's McKay River facility. As you can see, rather than using only exhaust gas for the heat recovery steam generator, a duct burner is added to increase the steam quality. In addition, rather than having a steam turbine for power generation, the steam is used for operational purposes such as an extraction system, downhole for in-situ recovery, or both. Now, just to circle back a bit in the presentation, and to clarify, when a coal power generation facility is converted to natural gas, they typically replace the coal burner with a gas burner for the boiler. They don't typically replace the burner and a steam turbine with a natural gas turbine. Now I'm going to pass it over to James from our London office.
Thank you very much, Joe. So my name's James Marks, as Robert said earlier. I've been adjusting for around 7 years or so, and I'd say a good proportion of the claims I've dealt with have been on gas turbines, primarily in the Middle East, where I have worked around the world. I will have to switch my camera off due to bandwidth issues, unfortunately, but you should be able to hear me fine. Okay, so what I'll be taking you through now is the function of a gas turbine and how it works, and some of the main components. So first of all, what is a gas turbine? Well, a gas turbine is in simplest form, it's a type of engine which can be used for either aero or industrial purposes. Aero purposes, I'm sure you're all familiar with. It's effectively a jet engine. So a jet engine is a type of gas turbine, we could say. For our purposes, though, we'll be looking purely for industrial uses. So for industrial uses, there's really three primary types of turbines we need to look at. The first is aeroderivatives. So as the name suggests, these are jet engines that have been modified for industrial use. They can often be skid mounted, and you may see them in gas, oil fields, things like that. The other type, or the second type I'd like to talk about is light industrial gas turbines. Similar to the aeroderivatives, they're often skid mounted, and as the name suggests, tend to be smaller. What I'd really like to focus on during this presentation is the heavy industrial gas turbines. So these are the ones you'll find in your power stations, much like the schematic of that combined cycle plant Joel showed you slightly earlier. And I think it's important to discuss gas turbines simply because despite the general move towards renewable energy, they're not going away anytime soon. I mean, in the UK, for example, between 40 to 50% of our electricity requirements come from combined cycle gas plants at any one time. And that's changed hugely since in the last 30 years or so when it was primarily coal. I mean, to put this into perspective, as Joel touched on, he mentioned the largest wind turbine on the market at the moment is 12 megawatts. The largest gas turbine on the market at the moment is 593 megawatts. That's a Siemens 9000 HL. To put that into perspective, that's about 800,000 horsepower in one single engine. So they create a truly enormous amount of power. Okay, next slide, please, Haley. Okay, so here is a schematic of a jet engine or a gas turbine. So there's three primary components you can probably see. On the left, you have the compressor, you then have the combustor, and you then have the turbine section. And effectively, in principle, it works in much the same way as your car engine. So you have your working fluid, which is air. This is compressed. It's then mixed with some type of fuel and ignited. And that is when you get your rapid expansion. So in the case of a car, that will drive a piston. In the case of a gas turbine, you can see here, that will drive the turbine section of the gas turbine, which you can see on the right there. Should be labelled yet. The gas turbine, the turbine section and the compressor are all linked on a single shaft. So the turbine is a set of rotating blades, which is driven by this rapidly expanding air. This is in turn connected to the compressor, which compresses that air in the first place. So if you imagine in a perfect frictionless world, you've had perpetual motion. As the turbine is driving the compressor, which is in turn driving the turbine. Fortunately, of course, we don't live in a frictionless world, and that's why we have to add some fuel source to keep this going. As you might imagine, this to keep this turbine in equilibrium, they have to start up and get to a certain speed, certain RPM before this equilibrium is achieved. So as a result, they do utilise starter motors, various types, hydraulic, electric, and pneumatic. Okay, so first I'd like to talk about the compressor. So you can see on the left side of the picture, this is the compressor, and it's made up of rows of rotating blades and rows of static blades. So the way it works is air is drawn into the inlets, which are on the left, and as they're labelled, they're air inlet. So the purpose of the air inlets is simply to channel the air in the right direction, make sure the flow is going in the right direction. The air is then drawn through the compressor into smaller and smaller sections. However, the functionality or the principle which the compressor works on is known as Bernoulli's principle. And this is the principle that pressure and flow have an inverse relationship. So as pressure decreases, flow increases. A good way to think about this is a balloon. So if you've got a balloon that's blown up, you release it, you get movement of air. However, the pressure is decreasing at the same rate. Next slide, please, Haley. Yeah, so here we are. So Bernoulli's principle. So it says that the speed of a moving fluid increases, the pressure within the fluid decreases. So what happens is the compressor compresses its working fluid, in this case air, by accelerating the air and then diffusing it to obtain a pressure increase. So effectively, we're speeding it up and slowing it down, speeding up and slowing it down. And that over multiple stages. The number of stages depends on the make and model of the gas turbine, but I'd say a typical heavy gas turbine, we're talking about 17 stages, something like that. That will increase the pressure to the stage where we need to get it. So each stage will increase the pressure slightly, usually about a 1-to-1 ratio, something like that. Again, very different for jet engines and industrial gas turbines. Depends on the function the turbine is designed for. Okay, so something I mentioned is that you do get different pressure ratios with jet engines designed for aerial use than you do for industrial gas turbines. One of the primary reasons for this is the materials used. So blades on a gas turbine will on a jet engine, sorry, will typically be made of titanium. And the primary reason for this is weight. Anything that goes in the air, weight is clearly absolutely critical. It's also very strong, very light, very strong. For industrial uses, they tend to be made of usually various stainless steel alloys, often coated by various aluminium slurries to prevent any kind of corrosion. I think the primary reason for this is simply cost. Titanium blades are extremely expensive. Less important if it's on the ground, the weight. So they tend to use stainless steel. As a result, the pressure ratios aren't generally so high. So the maximum pressure ratios you're looking at in aero purposes can be 1 to 40. The average, I would say, industrial gas turbine, heavy industrial gas turbine, you're looking at 1 to 17, something like that. So there is a significant difference. Next slide, please, Helen. Okay, so this is a General Electric turbine. It's the H-frame. It's extremely large. It's in various stages of undress, as you can see. On the left side of the picture, you can see the compressor. You can see each row of rotating blades there. What you can't see is the stator blades, which would fit in between each of these rows. The stator blades will be connected to the casing, which will fit very, very tightly across that compressor there. And towards the right of the picture, you can see the turbine section, those white blades there, and you can see the space where the combustor would fit. Okay, next slide, please, Henry. Yes, this is again another picture. This is a Siemens model here. So you can see on the right side of the picture, that's your compressor. So these are the rotating blades which are connected to the shaft, and then the casing would fit very tightly with the stators over the top of that, in between each row of rotating blades. I think you can see the gaps there where the combustors would fit, and then you can see the white blades. That is the turbine section, which we'll be discussing a bit later. Next slide, please, Haley. Yes, so this is just a photo of the casing, so you can see what the static blades look like. So they're connected to the casing, and you can see those sort of gaps where the rotating blades would be. When we're talking about stages, gas turbine stages, what we mean when we talk about stages, one row of rotating blades and one row of static blades. And as I mentioned, most industrial gas turbines, you look at something like 17 stages. It does vary, but that's a general ballpark figure. Okay, next slide, please, Haley. Okay, so we go back to our schematic of the jet engine here. So we've come through our compressor. So the air now comes out into the combustor. So you can see the third blue arrow there. I think that's known as the diffuser. So it looks like a funnel just before the air goes into the combustor. The purpose of the diffuser is to slow down this highly compressed air. So the air coming out of the compressor will be up to 150 meters a second, going into the combustor, and the combustor will have a continuously lit flame. So you can imagine that's like trying to keep a match lit in a hurricane. So the purpose of the diffuser, again, works on Bernoulli's principle, is to slow down the velocity to the optimum level before it goes into the combustor. Next slide, please, Haley. This is simply another schematic, and you can see the same thing. I think you can see the diffuser just after the compressor here, and then the air will go up into the combustor, which we'll be taking a bit more of a detailed look at now. Next slide, please, Haley. Okay, so this is a a combustor. It's actually from a 1950s Rolls-Royce turbojet engine. This has a central fuel compressor, which is slightly different from the ones we've been looking at previously. You won't see them so much anymore. I think this gives you a very good view of what a compressor would look like. So you can see from the right side of the picture, it's like a casing on the outside of the combustor, and that's where the airflow from the compressor will be coming through. And goes through those holes at the side of the compressor, where it's mixed with fuel. As the name suggests, gas turbines typically run off natural gas, although they can run off liquid fuels as well. In fact, most turbines can run off either, depending on operational requirements. You can also see the red hose there. That's your fuel supply, which will be injecting natural gas into that combustor. Combustors need to withstand extreme temperatures, as you might imagine. So we're talking over 2000 degrees centigrade sort of temperature you'll have in the combustor. So the combustor is generally manufactured from kinds of space-age materials, so usually super alloys with some kind of tungsten in it. As you imagine, that's not cheap. The materials used are very expensive. They often use ceramic for installation, and there will be various air cooling systems there as well. Okay, next slide, please, Haley. Okay, so when our compressed air has been mixed with the fuel and ignited, it will expand very rapidly. In a car engine, that would drive the piston up. In the case of a jet engine or a gas turbine, it will be used to spin these fan blades. And it's just like a fan a desk fan you might have. If you blow into a desk fan, it'll start spinning. Exactly the same principle. It's just very hot and moving at a tremendous velocity. Now, the first stage of the turbine section again has to withstand extreme temperatures. It's not quite as hot as the combustor, but we're still probably talking 1700 degrees centigrade, something like that. And so again, the materials it's manufactured from is absolutely critical. They tend to be nickel-based super alloys. They will then have thermal barrier coatings to insulate the base material. However, the melting point of the material which is used to construct these blades is actually still lower than the temperature it has to withstand. And as a result, they have to utilize air cooling. I think you can see on the left of the picture there, this is a cross section of what it looks like inside one of these blades. So cooling air comes from the compressor. When we say cooling air, it won't be cool. It'll still be about 700 degrees centigrade, but it'll be cool enough effectively to bring it below its melting point. So the air moves through the blade, through those passageways inside the blade, and then out the holes you can see on the picture on the right. And this effectively cocoons the blade in colder air, and therefore brings it below its melting point. As you can imagine, if there's any problems with airflow, anything like that, you're going to get blades overheating, and they will literally melt. And I certainly have seen claims where that has happened. The turbine section, because of the materials used, we generally call it the money section of the turbine. It's extremely expensive. Something like 60% of the cost of your typical turbine is generally in the turbine section. So if something does go wrong, I'm afraid there are going to be some rather large bills resulting from that. Okay, next slide, please, Haley. Okay, so now we've gone through the main components and how gas turbine works. Something I'd like to talk about is compressor failures. And the reason I'd like to focus on that is, and I admit this is purely anecdotal, but most of the failures I have seen tend to be on the compressor. Not entirely sure why that is, especially given the temperatures you see in other parts of the turbine, which you actually won't see in the compressor. But it does tend to be a very common area of failure, certainly in my experience. So the two most common reasons here are points probably 2 and 4 that you'll see on the slide here. So foreign object damage. So those rotating blades, depending on the frequency of electricity the country uses, will either be spinning at 3000 RPM or 3600 RPM. That's extremely quick. If you get anything in the any foreign object inside those rotating blades, it's going to destroy everything. There was actually a a story a few years back in Heathrow Airport. A elderly Chinese woman threw a bunch of coins in the front of a jet engine with the blades for luck. Apparently, fortunately, managed to shut. This was when it wasn't running. But if they had switched that on, all the blades in that turbine would have likely been destroyed. The second most common issue I've seen or I suppose it's part of the same issue really, is blade or stator liberation. If one of those blades in the compressor snaps off or comes loose, it's like going to get sucked through the compressor and effectively becomes a foreign object and causes foreign object damage itself. And something we'll discuss in a little bit more detail later is pitting corrosion, because that does tend to be, again, in my experience, the leading cause of this blade liberation. Okay, next slide, please, Haley. Okay, so pitting corrosion. So what is pitting corrosion? So it's a localized form of corrosion which cavities or holes are produced in the material, and they tend to be very, very small, and often very, very hard to see with the naked eye, actually. And they simply come from deposits on the blades in many cases, and a lot of this is due to the locations you see power plants. They're often in coastal areas because the cooling water needed, possibly in very industrial areas where you might have substances like sulfur, other just general chlorine-laden atmosphere. So if you get deposits in your blade, it can quickly lead to pitting corrosion. You can see sulfur and chlorine are some of the very common offenders there. Now, as you might imagine, the front of these compressors, where they're sucking in so much air, they do have filters, but you can't filter out everything. And really, the bigger the filter in front of your compressor, the more you're restricting airflow, which is actually restricting the top performance of the turbine. So that's always a trade-off there. Next slide, please, Haley. Yeah, as I mentioned, they're often very, very difficult to spot. Generally, a heavy industrial gas turbine will be running 24/7. Usually you'll have 2 outages throughout the year. You have a major inspection where the machine is opened up and they'll have a good look inside, and you've got a minor inspection. The minor inspection, they'll probably use some kind of borescope to have a look at what's going on inside the turbine and the compressor in particular. It's very, very difficult to spot any kind of cracking or pitting on using a borescope, simply because they do tend to be very small, and a borescope it's not always particularly clear. They also most power plants aren't going to want to open these turbines unless they know something's wrong. You can see the figure there. That's $2.5 million US. I must stress that is in the Middle East where costs tend to be higher. But for example, in Saudi Arabia, if you want to open up a heavy industrial turbine, that's the cost. That's the cost you'd be talking about. So they're not going to open these things, because of if, buts, and maybes. And we've got scheduled outages there, as I mentioned, that they will look for this sort of thing in major inspections, but it's hard to find, as I mentioned. Next slide, please, Haley. So this is the leading edge of a blade here. This is viewed under a microscope. It's about, I think it's 200 times magnification here. So as you can see, it's very, very small, and you'd probably really struggle to see that with the naked eye. So it just gives you a flavour of how small these pits can be when they start. Next slide, please, Haley. Once you've got your pit, it's effectively a small imperfection in the blade. If you can imagine, there's constant stress from all angles on these blades. Once you've got an imperfection, it usually doesn't take, because of the high cycle fatigue on the blades and just the stress in general, it doesn't take long for that imperfection to form a crack, which then can rapidly propagate through the blade, as we should see on the next slide. Show that, Haley. Yes, so this is, you can see the origin of the fracture down there on the right. So it's a very, very small pit there. That has slowly over time propagated throughout the blade, and that's evidenced by these beach marks, which you can see here. These I suppose almost like wavy sort of lines here, and that's indicative of high cycle fatigue. So once the crack has started, it's propagated throughout the blades, as you can see from the beach marks. It'll then get to a certain point through the blade. I don't know, let's say halfway through, where the blade can't take the stress and it snaps off. It then gets dragged through the compressor, and it may well damage several other blades, as I think we should be able to see on the next slide. Yeah, so this is the result. So these blades are spinning incredibly quickly. One of them has come off, got dragged through the compressor, and is destroyed. You know, it's not uncommon to see it destroy all the blades in the turbine. Next slide, please, Hope. Yeah, again, this is another photo. It's the result of a blade coming loose. As you can see, I mean, all of those blades have been destroyed. They're all going to need replacing. So as a result of one blade coming loose, you're going to need a full set of blades and stators as well, because obviously we're just looking at the spinning, rotating blades here. The blades on the stator blades on the casing would likely be in a similar condition. Okay, next slide, please, Ellie. So there's various mitigating strategies which I won't spend too much time over. The two primary ones I've seen are offline and online. So offline washing, you've obviously got to shut the turbine down and you wash it to remove all the accumulated deposits. As I said here, proper drying is essential. When you're washing these pits or these corrosive elements off your blades, what you're doing is you're obviously introducing water, which is another element that can cause corrosion. So it's very crucial that proper drying happens. Otherwise, you can actually make the situation worse. You've also got online washing, which is where the blades will be rotated very slowly with the ambient temperature above a certain level, and yeah, washed. Okay, next slide, please, Haley. Okay, policy coverage. So again, this is drawn from my experience, which is primarily in the Middle East. I believe I'm correct in saying most of this is true for Canada as well. But yeah, so what I generally see, and we're talking the insureds here are usually the power stations themselves. They tend to be all risks. So the onus is on the insurer to demonstrate if a loss is not covered. Business interruption. Generally on these claims, you'll find the business interruption tends to actually dwarf the property damage. In the Middle East, you typically see what's called power water purchase agreements. In Canada, I suspect that'll be power purchase agreements. In the Middle East, often alongside power plants, you get water production. You certainly won't see that in Canada. Something we've talked about a bit is the pitting corrosion. Now, some of you might be thinking that obviously corrosion tends to be excluded, and you would of course be correct. However, resultant damage is often covered. So you may be able to exclude the single blade that came loose as a result of the pitting corrosion. However, the several hundred it destroys on the way through the compressor may well be covered. Generally, in my experience, you get coverage for RCA investigations, which is something I'll talk about in a little bit, because you do have to be careful there. And contractors tend to be covered as well. Usually you'll see hold harnesses with contractors. So if something goes wrong during repairs, you may not necessarily have an avenue of recovery against your contractor. Okay, next slide, please, Hayden. So these are some of the adjusting issues which I've come across in my time adjusting gas turbine claims. The first issue is the RCA costs. I've frequently seen claims where root cause analysis costs have just spiraled out of control. And that's because rather than a root cause analysis, it's rapidly moving into R&D territory. And that's something you need to be aware of. So obviously we're interested in the cause as far as determining coverage, but beyond that possibly should not be for insurers' account. Obtaining information from original equipment manufacturers. Gas turbine manufacturers, it's an extremely competitive business. They generally don't like providing a lot of technical information, which you may need. And it's very usual for the adjuster involved to be asked to sign a non-disclosure agreement to actually obtain a lot of this information. And if you've got a BI loss, all this does tend to delay the process. It's worth remembering that the insurers tend to be the power stations, certainly in my experience. Manufacturers don't necessarily have the incentive to cooperate or certainly do things quickly. Difficulties within the supply chain and long lead times. Most manufacturers don't carry huge stocks of spare parts, and neither do the power stations themselves. So let's, for example, you had a blade came loose, got stuck to your compressor and destroyed all the other blades. You go to your manufacturer, be that Siemens or General Electric, you may well find they actually don't have a full set of blades in stock. They have to manufacture them from scratch. You may have to get in line because they may have other orders. So long lead times are common, and it's these long lead times that often lead to high business interruption costs. Lack of suitable contractors, this probably isn't so much of an issue in Canada, but certain countries you may not have the contractors to deal with the situation. Customs delays, again, might not be such an issue in Canada. I mean, so for example, I was dealing with a case in Iraq actually, where a new set of blades was ordered. They tried to get it through customs. The customs guard booted a hole in the side of the crate, had a look what was inside. They then left it sitting in a yard somewhere for a number of weeks, completely exposed to the elements. It rained, and these blades ended up getting corroded, and we had to find a new set of blades. Clean conditions failures. So again, another case I was working on. This was actually a steam turbine. So steam turbine had a damaged set of blades. New blades were sourced. They were all installed. Everything was going smoothly. The power plant switched everything on again, and within 4 seconds, all the blades had been shredded. We then discovered upon opening the turbine up, one of the contractors had left a spanner inside the turbine, so that acted like a foreign object and destroyed the blades. As I mentioned, the contractors were covered under the policy, so there was no recourse for insurers there. Payments on account, because we're generally looking at fairly high BI costs, and most insurers will ask for payments on account, and that's just something to be aware of, really. The other issue we have from an adjusting perspective is BI mitigation. As I'm sure you're aware, the insurer does have a duty to minimise those business interruption costs, and there's various methods of doing that. One of the common ones we see is they move scheduled outage. So they generally, as I mentioned, have one major outage and one minor outage throughout the year. If they can move that to when the turbine's going to be out anyway, then they may be able to minimise that loss. Okay, so guys, I hope that gave you a good overview of how gas turbines work and some of the common issues we run into as adjusters. So I'm going to now hand over to Bob, who's going to take you through some cases he's worked on.
Okay, thanks, James. Again, my name is Bob Moore. I'm Managing Director for Charles Taylor here in Canada. I thought I would, I'm actually sitting in the middle of the foothills of the Rockies here, and we're in the middle of a snowstorm, which affects the satellite feed here. So I'm gonna get rid of my video, and we'll just use the audio, just so hopefully we don't get any interruptions here. It's a pleasure to work with Joel and James here. I think we all three of us qualify as turbine geeks. You know, if you look at the design and assembly and the materials involved, the science involved with turbines, I think they're truly spectacular pieces of engineering. If you haven't seen one, and if you ever get a chance to see one that is unbuttoned so you can see the internals, don't pass up on it. They are a truly amazing piece of equipment. Most of the losses that I see, James gave you a bit of an overview in terms of common causes, but the ones that I see for the most part are, unfortunately, one of the common ones is run to failure. So these things have a limited life, and if the maintenance isn't kept up on them, they can fail just from simple use. Oil starvation, so startup, shut down. There is a very clear sequence for these things to be started up and shut down. Ingestion of foreign materials is another common cause, and blade failures. If there's any defects in the construction of the blades, they can fail. So the loss that I was going to talk about is a situation where a maintenance provider is working on a third-party turbine. The turbine itself is used to produce high-quality steam, which is sold to an oil sands producer in Alberta, and it also provides electricity to the oil sands producer, and any excess electricity is sold into the grid in Alberta. Next slide, Haley. We'll go to the next one after that. So during some routine maintenance, the maintenance provider was replacing the control logic system. It was an older turbine. The software that was in it was no longer being supported, so they're updating the software. And part of that job also included the replacement of a gas control valve. So they finished the work. They restarted the unit. They couldn't get it to run properly at the appropriate speed. They went through about 6 attempts, 538 minutes of runtime, and they just couldn't get it to do what they wanted to. So they started to recheck the work they did, and they also borescoped the internals of the turbine. And what they found was in the combustion section, there was severe heat damage. So they opened up the turbine, and they found that the liners and flow sleeves, which are in the combustion section, were severely damaged. Next slide. So what you're seeing here are the flow sleeves. So you'll recall from James's some of his images, alongside the combustion section, you have these flow sleeves, which essentially are the where oxygen or the air that is going into the inlet and the fuel mix, and that goes into your combustion section of the turbine to produce the energy. So what happened here is the flow sleeves were severely damaged due to heat. Let's carry on to the next one. Actually, just on this slide for a minute here, you can see, sorry, just go back for a second. You can see the sleeves are on the left, but if you look at the picture on the right-hand side, you'll see these two objects that saddle the turbine. Those are where the flow sleeves sit in relation to the turbine itself. Okay, next one. So what happens when things go tilt within the turbine is everything goes out of alignment, and you get a lot of abrasion damage. So what you're seeing here in the photograph on the left is the first stage shroud block, where the blades have clearly gone out of alignment and come into contact with a stationary piece of the turbine. And the metal that you saw disappearing from the flow sleeves melts, and it has to go through the flow path. And in this case, it impacted the veins in the combustion section, at which point it solidifies and adheres to the blades themselves. So, next one. So what happened here in the cause investigation, we had an RCA completed by an independent turbine expert, and he essentially identified that the gas control valve was the incorrect model, and it had been, and because of that, it was incorrectly calibrated. So when they tried to start it up, normally these things go in stages in terms of how much fuel, how much air, and it has to be precisely metered out. So in this case, they had excess fuel that went into those liners, which caused excess heat, and with the flow not being sufficient enough, airflow not being sufficient enough, it essentially exceeded the melting point of the sleeves themselves. Next one. So when you added all all of the costs associated with this, this is essentially what we got. We got the turbine repairs themselves were 3.7 million. The lost steam sales to the oil sands producer. So again, the oil sands producer pays for high quality steam. It's part of the oil sands extraction process. Lost sales about 400,000. They had to, because they had a contractual commitment, the maintainer had to provide replacement steam, or they chose to provide replacement steam in this case. There was lost electricity sales to the oil sands producer, which was used to run their refinery. And there was they had to replace that electricity, again 1.9 million. And then they had lost sales into the grid, which was about 1.5 million. So all told, about $10 million. So relatively high value claim. Next slide, Hill. So I'm not going to read the policy terms. I think it's sufficient to say that they had an occurrence which caused damage, and in terms of the meaning of the word damage within the policy, most everything that I just listed off in the damage section would have actually been covered. So they didn't have any contractual liability exclusions, no your work exclusions or your product exclusions. It was probably one of the broader policies that I've ever seen. One of the reasons why I chose this case to look at is that the maintenance provider who was doing the work on the turbine had a long-term service agreement with the owner of the turbine. They did not want that contract interrupted in any way. So there was actually no contact between Charles Taylor Adjusting and the owner of the turbine. All of the discussions took place between the insured, Charles Taylor, and the insurer. And I'll get into that in a little bit more in a minute. Next slide. So if you were going to look at all of the contracts involved, what we would look at is obviously the policy. And when we looked at that, again, there was no exclusionary language. And all that needed to be established was legal liability with respect to an error made by the maintenance contractor. So we looked at the long-term service agreement, which is an agreement between the owner of the turbine and the insured. And in that contract, there was no obligation to respond to consequential losses. Their only responsibility was to repair the property that they were working on and/or had resultant damage to it. There were also contracts between the turbine owner and the oil sands producer, the turbine owner and the grid. We didn't need to look at those because the long-term service agreement excluded consequential damage. So next slide. So the loss settlement itself, it is part of the reason why we brought this particular case to you folks is that we're seeing more and more of this, where maintenance or service providers have these long-term agreements. They are incredibly valuable to the maintenance provider, and they don't want any interruption with the communication with their client. So in this case, what happened was the insured reached a commercial settlement with the turbine owner with respect to any business interruption. So we were aware of it. We had a good idea of what it was worth. They had no obligation to pay anything, but to provide some continuity to the contract, the long-term service agreement, and keep on good terms with their clients. They decided to come to an agreement. And there's usually some discussion between the adjuster, the insurers, just to make sure everybody's on the same wavelength in terms of which direction that goes. The investigation of cause actually confirmed that the owner was somewhat responsible for the error in calibrating the gas control valve. It had to do so with some changes to the OEM requirements or specifications for the turbine, which the maintenance provider were unaware of. So liability was assessed at about 50% against the insured, and we were able to agree that between the insured to move forward with that. So what happened at the end, we reached a settlement for 50% of the turbine repairs, less salvage. Those liners that you looked at were worth about $400,000, and a number of them were still usable, just needed to be refurbished. So we took that out. A relatively high policy deductible, so out of 9.8 million in potential damages, the loss was settled for about 1.1. Had there been a your work product exclusion in the policy, it probably would have reduced the overall settlement possibly by about $60,000. That would have been a replacement valve and recalibration. So next slide. I think we're pretty close to the end there. We are at the end. So not sure if we have any questions or what have you, but Haley, if you can take us through that. Thank you, everyone.
I'll jump in here, Bob. Thanks so much for that. Really appreciate it. Just on the continuing education credits, the email address here is for Andrea Scallion. If you could email her to get your Alberta CE credits, that would be great. Please ensure in your email that you include your CIPR number. That just speeds up the process quite a bit. So I think we do have a few questions here. So if the presenters want to bring up their webcams, we can give that a go. But the first few of them, it looks like, are actually for James. And the first one was, what are OEM recommended inspection procedure and intervals to prevent corrosion?
I mean, the general, in my experience, it tends to be one major outage and one minor outage throughout the year. Again, it's my experience. I presume that will vary depending on make and model, but that certainly seems to be the standard in my experience.
Okay, great. The other one was in your presentation you mentioned RCA, and the question was, what was that? I believe that's root cause analysis, but
yes, apologies. I should have explained that in a bit more detail. Yes, that's a root cause analysis. So as I mentioned, often these policies will have clauses which will pay for any kind of root cause investigation, which will almost certainly take place if there is a serious incident.
Okay, great. And then another one here is the person who's actually encountered problems with white etch cracking on turbine bearing failures, and they wondered what the ramifications of this type of damage on all risk policy cover is.
It's very fortuitous you mentioned this, because I've never actually seen this on a gas turbine, but I've seen it on multiple wind turbines. Where it's currently in the UK, it's going through the legal system at the moment. Actually, we're currently taking legal advice as to whether white etch cracking should be covered. For those of you that aren't aware, white etch cracking it's something that's newly been discovered in the last 15 years or so, and you know, very little is known about it. What causes it? We know it's some type of accelerated fatigue cracking. But the underlying causes are still relatively unknown. That's still subject of debate amongst sort of engineers and experts. Yeah, I suppose it really depends on the policy wording. But I certainly have seen white etch cracking cases on wind turbines. I have seen them get paid. I hope that sort of answers your question.
You see is there is some case law in Canada that talks, and again, everything obviously goes back to the specific wording, and sometimes you see corrosion as a standalone word in the exclusionary language. We've also seen policies that have the words normal corrosion in front of the word corrosion. So I would hazard a guess without making any legal statements at all that what we're describing here is probably not normal corrosion.
Yeah.
At this point. So.
Mm-hmm. Okay. There's a question for you, I believe, Bob, here. And it was, did the insured implement a management of change protocol as a result of this incident?
Normally, if you, and James can probably speak to this a little better than I can, but normally with every turbine, there is a log. Anything that happens to that turbine is written up in the log. So if you're a repairer and you go in, that would be the first thing that I would ask to see. Let me have a look at your log for all of the activity on this turbine from the day that it was installed. And in the case of this gas valve, would they have picked up the fact it was a pretty minor change that was made, and I wouldn't have expected the service provider to necessarily pick up on it. And you know, you get changes of staff and what have you, and not everything gets into the book. But I guess to answer the question succinctly, there should be that document that sits in the facility and is available for anybody to look at who's going to work on the turbine. I don't know, James, what's your experience on that?
Something I would add is that certain manufacturers, I know General Electric in particular, do this. They issue periodically what's called as technical information leaflets or technical information letters. And what they are is this is when a potential fault has been identified with this make and model of turbine. This information leaflet is issued to all owners and users of this turbine with make recommended changes. We've detected the problem with XYZ. We reckon you do ABC. So it may well be these certain issues that happen in one power plant. This make and model of turbine, all the owners would have a recommendation to make some kind of change. Although that would have to be, I think, a fairly major issue for that to happen. But yeah, we do periodically see these tills as they're known go out.
There was actually a follow-up to that question, which was the reason for the question as well, because it was not a like-for-like valve replacement.
No, it was not.
Mm-hmm.
Sorry, maybe clarify on that. They put the same valve back in, and because they changed the control logic, it should have been a valve that, I'm not sure if it's the same valve or not, but the calibration was different. So with the way that the logic worked on with the new logic control, there should have been less fuel at that at that point in the startup sequence. Not sure that answers the question, but.
Okay. It looks like we're getting a few more questions coming in here. Oh, yes, that does clarify the question. That's great. We've got another question here. Were the resonant vibration failure subrogated to the OEM?
I must admit I've not seen a resonant vibration failure that was subrogated to the OEM. I think generally what you would see, because clearly they designed these turbines, they're not supposed to be operating within their natural frequency. So you would expect these resonant failures should not be happening unless there's some kind of external force sort of acting on the turbine, which is causing it to operate within its resonant with its natural frequency. Potentially, I suppose you could, but I can't honestly, hand on heart, say I've seen it happen. No.
Okay. You seen anything along those lines, Joe?
No, I haven't. And I agree with James. Like the OEM would have designed the turbines to operate outside of that resonant frequency. So if I was the OEM, I'd be going back to the operator saying, okay, well, let me see your operation logs, because obviously you've done something wrong to put the turbine in that situation.
And so something I would add is when you see these root cause investigations, it's quite rare you get some nice, neat causation. Usually what will happen is you'll have 7 or 8 factors which are all contributing to the failure. It may be quite difficult to go back to your manufacturer and subrogate if it's one factor of, let's say, 7 or 8 which have contributed to this. Unfortunately, it's just the nature of these claims. You very rarely get a nice, neat, singular cause. It tends to be multiple factors which have gone into it.
Okay, that's great. We don't actually have any more questions, which is good because we are actually 5 minutes over already. But if anybody does have any additional questions, you can please just send us an email and we'll get back to those. And when we send the email tomorrow, which will have a copy of this presentation recorded on there, we'll include any answers to questions that come in after the. Also, you might be able to see on there that you can download the bios of the presenters. If you're not able to do that, we will include that in the handout tomorrow as well. Okay, well, thanks everybody so much for attending today, and thanks for all of our presenters. It was very, very interesting, and we look forward to seeing you all for our next presentation coming up in the next month or two. Thanks so much. Bye-bye.
Thanks, guys.
Everyone.